think was mentioned in the review chapter in terms of roots. You can break things up like that. Now, this, in turn, again, following the rules, you can break it up into the root of -1 times the root of p. And the root of -1 we just identified as I, so we can actually write this as I times the root of p. And that's how we deal with negative numbers under the root sign, and we start to work with what we call these complex numbers. Just a couple quick examples. These are from the textbook. The directions are to express each number in terms of I. So for example, if we had the square root of -16, we could write this as the square root of -1 times 16, which can be written as the square root of -1 times the square root of 16. Substituting I for -1, you can write it as I times the square root of 16 is 4. And then, of course, we can rewrite this as 4I. You want your constant before the I whenever possible. Another example might be the opposite of the square root of -13. This would be the opposite of the square root of -1 times the square root of 13. I just broke it off. I took one less step. This is I, so we would have the opposite of I times square root 13. Obviously, 13 is prime, so there is no square root. Okay, so again, there are a number of examples in the text. I would probably just take a look at those and make sure you know how to work them. Now, taking a second to delve further into what we just called a complex number, let's go ahead and define it formally. So, hold on one second, let me get another marker. Okay, my apologies. Still working on this videotaping thing. It's pretty tough not to have an audience, so. Okay, a complex number is a number of the form A plus BI. This form is pretty important, and what I need you to notice is that there are two parts to the number. Okay? First of all, A and B are real numbers. The number A is the real part of the complex number, and the number B is the imaginary part of the number. So, what's interesting is that because A and B are both real numbers, either one can take on the value of 0. So we're used to seeing numbers where B takes on the value of 0, because when B is 0, the imaginary part goes away, and all we're left with are all of the real numbers that we're used to working with. When A takes on the value of 0, we have only an imaginary part of the number, of a complex number that we're working with. And there's a really interesting relationship tree, I guess if you want to call it, on page in the textbook on page 236. And it might be worth your time to take a look at how all of the different sets of numbers are related. So up to this point, all of the numbers that we have talked about are complex numbers. From there, you break off into the set of real numbers and then the set of imaginary numbers, or complex numbers, I guess is what we call them. And then from there, the tree continues to move down. You should have taken a look at number sets in the review chapter. I think it was one of the first things in the review chapter. Okay, continuing on. Now, when we start talking about operations with complex numbers, your operations behave in the same way that operations with variables would. So when you add or subtract complex numbers, you're looking to collect like terms, and all the i's are like terms, all the real parts are like terms. When you talk about multiplying and dividing with complex numbers, you I guess initially we can say treat the I as a regular variable, so I times I would be I squared, etc. And then you want to come back to that relationship where we said I was equal to the square root of -1 and I squared was -1. So at the end you come back and substitute those values for I, or I for those values. So just a couple quick examples. If we had 8 plus 6i plus 3 plus 2i, this is an example where we're adding complex numbers, so you collect the like terms. We're going to collect the real parts first. So 8 plus 3 is 11. Then you have 6i plus 2i, which is 8i. At this point, you're done. You have a new complex number that has both a real part and an imaginary part. And although complex numbers don't require both parts being present, we started with both parts, we should probably end with both parts most of the time. Another example might be 1 plus 2i times 1 plus 3i. So this would be a case where we FOIL, treat the i's as variables initially, so 1 times 1 is 1, 2i and 3i is 5i, and then you have plus 6i squared. But remember this relationship, I squared is -1, so what we have is 1 plus 5i minus 6. When you substitute -1 times 6 is -6. And then you combine the two real parts here. So you have -5 plus 5i. And again, just to maintain the standard, you always put your real part first and then the imaginary part is the second piece. Okay, the conjugate of a complex number a plus bi is a minus bi. And conjugates are useful because the product of conjugates yields a real number. And keeping with what is standard, you often don't leave imaginary numbers in the denominator of rational expressions. You often want to make sure that the denominators are real numbers. So if you have a complex number in the denominator of a rational fraction, the way to get rid of it is to multiply the numerator and denominator by the conjugate of the denominator. And that's sort of a mouthful, so let me try and find an example here to show you. example 6, it says to divide 2 minus 5i by 1 minus 6i. So the problem here is that we have a complex number in the denominator. So what we're going to do to make that real is multiply by the conjugate. Okay? So clearly we're going to be foiling the numerator and denominator. So in the numerator you have 2 minus 5i plus 12i, which is 7i, minus 30i squared. I hope that's correct. Yeah, that's correct at this point. And then divided by 1, minus 6i plus 6i go away, so you end up with minus 36i squared. So again, you take this I squared and you go back to this relationship that I squared is equal to negative 1. So what you end up with is plus 30 plus 2, so 32 plus 7i, divided by, this turns into plus 36, so divided by 37. Now, again, it's pretty typical to break complex numbers up into a real part and an imaginary part. So I'm sure you can follow all this. This is pretty simple. But the last step would then be to say, okay, well, the real part is actually 32 37ths. The imaginary part would be 7i divided by 37. So make sure you have a real part and an imaginary part. All right, the last thing to note in the first section, I don't know how low you can see the board, so let me erase this